Welcome back to the last section of Chapter 6. This section is a little bit different from the rest of the chapter because we're not looking at finding the area or volume, although we will be integrating. So it is possible that you could have a volume question or an area question set up where you need to do this. But this isn't an application as much as it is a technique. Today we're going to be looking at integration by parts. And this is the first of the BC only topics, by the way. We'll get a couple of them sprinkled in before we're fully into only BC topics. Anyway, integration by parts relates directly with the product rule. If we remember the product rule says that if we have a function f of x, g of x, and we want to take the derivative of that, d dx of this guy, we're going to get f of x, g prime of x, plus f prime of x, g of x. Or if we take the derivative of uv, we get u dv plus v du. So that's the product rule. That's with deriving, finding the derivative. Well, what does that do for us for integrating? Well, if we wanted to integrate this, we would integrate both sides. And we get dx, we get dx here. And so we could integrate both sides, simplifying a little bit. We're not going to be able to simplify all that much, but simplifying a little bit. This side, the integral and the derivative cancel themselves out. So we're back to the initial equation, f of x, g of x. Over here, on the other side, we can split it up at the addition. So we can have f of x, g of x is the integral of f of x, g prime of x, dx, plus the integral of f prime of x, g of x, dx. All right, so we have our function, our product equals this great big thing equaling integrals. All right, we're going to solve a little bit more. We're going to take one of these guys. We'll take that one, and we're going to subtract it over to the other side, which leaves this one, the integral of f of x, g prime of x, dx equals the original product, f of x, g of x, minus this other integral, the integral of f prime of x, g of x, dx. Or in the u terms, the integral of u dv will equal uv minus the integral of v du. And so to solve problems with these, to integrate these, we are going to find u and dv, and then we can find the other one, and then plug it into the formula. It's going to look a lot like the product and quotient rule because we'll be using like the u's and the v's. The trick to integration by parts is your selection of u and dv. U should be something that when you take the derivative, it's going to get smaller. dv should be something that's easily integratable, and when you take the antiderivative, it doesn't get bigger. Things that fall into that category would be things like sine and cosine. e to the x doesn't get bigger. Things like that, where it either stays the same or it kind of goes in circles. Sometimes, and we'll see an example of this, sometimes your dv will just be dx. The whole rest of it's going to be u. So we'll see what that looks like. The other deal with integration by parts is sometimes, so we'd plug everything in. This one's easy, you just have to multiply those. And then you have to find the antiderivative, the integral, of this one. Sometimes it's super easy, and you can do it on the very first one. Sometimes this is going to take more integration by parts. Sometimes, if you have sine and cosine in the right way, this will actually equal this after 2 rotations, and you can subtract it over and divide by the constant. So let's take a look at an example of what one of these could look like. Let's find the antiderivative of, we'll go x e to the x dx. So this is not something that we can just take the antiderivative of because we don't have a derivative that equals this. That's where integration by parts comes in. So in this case, I would make u equal to x and dv equal to e to the x dx. So u equals x, dv equals e to the x dx, which means du will just be dx, and v, the antiderivative of e to the x, is just e to the x. There will be a plus c in here, but I wouldn't throw it in yet. Put it at the end of the answer. Don't worry about it in the u's and the v's. So now, if you remember, the equation is going to be u times v. That'll be x e to the x minus the antiderivative of v du. That's e to the x dx. Now what's the antiderivative of e to the x? We already found it once, it's just e to the x. So this will be x e to the x minus e to the x, and this is where you'd put your plus c. So there we go. That's the antiderivative of x e to the x. If we had something like the antiderivative of x squared e to the x dx, that's going to be, u would be x squared, dv is still going to be e to the x dx, so v is still e to the x, but du will be 2x dx. Plug it in. We'll have x squared e to the x minus the antiderivative of e to the x times 2x dx. I'm going to put the 2 out in front. E to the x times x e to the x dx. We can't just take the antiderivative of that. This is where we would have to do it again. I would look, that's what we already found over here, right? So the antiderivative of that's still going to be this. Again, we would get through it just with integration by parts, just inside the question. You might have to do it a couple times. I didn't say it was going to be pleasant, but this is how we can find the antiderivative of things that we just don't know the derivative of. So this is going to go in there. So this is going to end up equaling x squared e to the x minus 2 times x e to the x minus e to the x plus c. The plus c doesn't have to be on the inside because 2 times a constant is still an unknown constant. But I would distribute this just because x squared e to the x minus 2x e to the x minus 2 e to the x plus c. So other things these problems could do is it could give you an initial condition where you could find c, no different than anything we've done in the past. We could do a definite integral. At first I had direct stuck in my head. I'm like, that's not right. That's not the word that wants to come out of my mouth. We could do a definite integral where if we had let's say we went from 0 to 1. All right, that's fine. We would just plug in 1 minus plug in 0. So in this case, we would have 1 squared times e to the 1, so that's just e to the 1, minus 2e to the 1, which is just e, minus another 2e, right, minus plug in 0. Let's see, that first one's going to be 0, minus 0, minus 2, because e to the 0 is 1. And then combine our like terms. We have e minus 2e, that's going to be negative 3e, minus negative 2 is plus 2. So if we have a definite integral, we do it the exact same as we do any other definite integrals. Use the fundamental theorem of calculus, find the antiderivative, plug in the big one, minus plug in the little one. That's what we've got. Another time when integration by parts is very useful is when we have something like natural log x dx. Or could be things like inverse tangent of x dx, inverse sine of x, anything like that. You might be looking at it thinking like, well, where are the parts? And well, the integral of natural log of x doesn't seem that hard. Natural log x is 1 over x. That's the derivative. We've never done the integral of natural log x, at least not by hand. We've had the calculator do it for us, but with integration by parts, these questions could be on a non-calculator part of the test. So how do we do it? Well, we only have one part pretty much, the natural log x. If we can't just find we wouldn't want to make that the dv, because if we did, we'd have to find the antiderivative of it, and we can't find the antiderivative of it. That's the problem. So we'll make u equal to the natural log of x, which means dv is everything else, which is just dx. This one would be set up the same way, by the way. Antiderivative, or derivative of ln u, ln x is 1 over x dx. The antiderivative of dx, v will just be x. So we can plug it into the equation. U times v, that'll be x ln x, minus the antiderivative of v times du, that's going to be x times 1 over x dx. These guys cancel to make 1. The antiderivative of 1 dx is just x. Let's see, so we have x ln x minus x plus c. That's the antiderivative of a natural log. So this is how the integration by parts technique gets used. It's all about the equation UdV, the antiderivative of UdV equals UV minus the antiderivative of V du. We plug it into there so that we can find the antiderivative. So again, that's integration by parts. Practice. This takes practice. Remember, the U and dV selection is half the battle to this. Making sure that you have the right ones in the right place. So keep working problems, keep asking questions, and as always, happy mathing.